Today we're going to talk a bit about the history of Asteroid Day and continue furthermore about what it is about and why do we care about asteroids. So it all started in the year 2014 when the Asteroid Day was co-founded by the astrophysicist Dr. Brian May. Most probably most of you know him because he's a very well-known, very famous musician of the Queen rock band. He was a guitarist. And the next guy was Rusty Weisskart, an astronaut of the Apollo 9 mission. And Danny Garimai, who is the president of B612 Foundation. And my very good friend Greg Richters, who is actually a German filmmaker. And he created the film 51 Degrees North, which actually was one of the main reasons that this asteroid day was founded. So our initial idea was to educate the public about the importance of asteroids, but also entertain them and learn about their roles in the formation of our solar system and so on. So this asteroid day, it emphasizes the great impact of asteroids in the recorded history of Earth, and mainly marks the anniversary of the 1908 Tunguska event. The Tunguska event where we had an asteroid impact, never hit the ground, but exploded above the ground, devastating a very large area. We'll see about it. We'll talk about it in a few minutes. So in the year 2016, so with the leadership of the Asteroid Day Initiative, with the leadership of the Association of Space Explorers, and the United Nations officially designated the Asteroid Day as the International Day of Awareness and Education about asteroids and their impact hazard. So it's very important that the United Nations actually is celebrating as an international day because it shows the importance of it. And having in mind the Tunguska impact over Siberia, 1908, it means that it could actually happen anytime without knowing, and we need to raise the public awareness about these asteroid impact hazards. And this asteroid day now has a steering committee, and all the national coordinators are also coordinated by a global coordinator, my friend Saulo Mahado from Brazil. So he's the guy who is running after us to register our events and organize some things. So before I continue further on, I will share another screen, which is a very short video regarding this asteroid day initial. Sorry. Oh, okay. Yeah. Are you able to see this? Really? Yes. Sharing, yes? Okay.
So I want to emphasize that Asteroid Day is a movement to float all boats.
Asteroid Day began in 2015, gathering the best and brightest asteroid experts, together with a large community of concerned citizens.
I've known some of the people behind Asteroid Day for quite a number of years, and they're smart people. So when they asked if I would help, I took it very seriously.
Through the collaboration of Brian May, astrophysicist and legendary guitarist and songwriter for Queen, and Greg Richters, director of 51 Degrees North, a sci-fi thriller about an asteroid impact. They enlisted the expertise of Apollo 9 astronaut Rusty Schweickart and Silicon Valley operative Danica Remy to grow the movement to tens of thousands of supporters. In just the first year, scores of astronauts, notable scientists, artists, and leading astronomers launched Asteroid Day by creating independently organized events at schools, museums, science centers, astronomy clubs, and in film and on television. Asteroid Day engages millions of people worldwide in support of increased efforts to find hazardous asteroids. Before hazardous asteroids find us. Asteroid Day. The dinosaurs never saw that asteroid coming. What's our excuse?
So, what is our excuse? Do you have an excuse? Anyone? Can you hear me?
I can hear you.
Okay.
Yes.
I have no
We have no
excuse.
excuse. Since we have technologies that are able to track, that we are able to communicate with scientists around the world, then we have no excuse. So the mission of the Asteroid Day is the dynamic awareness and educational programs to inspire the world about Asteroid Day. So we organized a lot of different events, and especially us, the coordinators, we share the word with many local clubs, and actually we share it to everyone, to clubs, to planetarium, to local astronomy clubs, to science centers, to municipalities, because we have to open the ears of the government to listen to us. So we're hosting these events, we share educational resources, we share our knowledge and experience in event organizing, and share our expertise. So we're looking for the role of the asteroids in the formation of the universe, how we can use their resources, why asteroids can pave the way for future exploration, and how we can protect our planet from asteroid impact. And there is a project, Nearshoot 2 project, we're going to talk about it a bit later. Now, after this day was founded, we thought about increasing the awareness in such a way that we will involve as many scientists, engineers, artists, I don't know, academicians, technologists, and so on. So we have created the Asteroid Day 100 Times Declaration. Now, since we know that we have a very large number of asteroids, an incredibly large number of asteroids, have the potential of impacting the Earth, and we have an approximation of 1% of the only discovered up to now. Okay, and so this 100 Times Declaration calls for the use of the available technologies to detect and monitor asteroids near the Earth that threaten human populations, and multiplies the speed of discovery and localization of asteroids near Earth, the so-called near-Earth objects. So the purpose of this 100 Times Declaration, okay, is to be increased by 100 times per year within the next 10 years, okay, from the day of the we funded this initiative. So let's talk a bit about the Tunguska event. So here we have a map, and we have the arrow, of course, and this is the area that was impacted on the 30th of June 1908. That's why we celebrate. Okay, we don't celebrate the devastation of an impact created by an impact, but we commemorate this event every year on the 30th of June 1908 was the first this event, but every year we celebrate on the 30th of June the International Asteroid Day. So in this place over Siberia, we had this impact, and actually there is an impact without a crater. It was affected at a radius of 25 kilometers, so a diameter of 50 kilometers. And there was a newspaper that mentioned that somewhere a man was ejected from his house porch 60 kilometers away from the wave that was created from the impact. The impact explosion was heard 1,000 kilometers away. And the asteroid diameter is estimated to have been around 80 meters. And it was traveling at the speed of 80,000 kilometers per hour. A very, very fast actually. So this was the result. This was the devastation in the forest of Tunguska over Siberia. So as you can see in the picture, the trees fell down because of the impact. 80 kilometers diameter forest was destroyed. Now, if we are talking about asteroids, we are talking about the remnants from the formation of our own solar system. And if we are talking about the main asteroid belt, we are talking about the area found between Mars and Jupiter. And we also have the Trojan asteroids near the orbit of Jupiter. So what is important about asteroids? Why do we want to track them? Of course, we want to track them to try to protect ourselves, our planet, from future impacts. We have to try and find ways how to redirect them or to destroy them before the impact. But why are they important also to study? Because they can give us evidence about the origins of our solar system, since they are considered parts of the early stages of our solar system. We have to understand the origin of life on our planet. In meteorites, we have discovered, if I may say it in simple language, parts of DNA and RNA. So if we have all these compositions mixed together at the appropriate environment, then who knows, we could start getting life again. So another thing is mining of near-Earth asteroids. We may mine them for water, but especially for metals, precious metals. So this initiative grew the interest of many countries in the world, and as you have seen, we started with 86 countries in 2015, and Asteroid Day Cyprus was one of the countries that was interested. It was my initiative to join this global movement, and actually was suggested by colleagues from the Astronomers Without Borders to become the national coordinator for Asteroid Day, as well as I served, as they have considered that I was serving the Astronomers Without Borders very well, and we were very active. So I accepted this. So I became the national coordinator for Cyprus as well. I believe we're doing well. We're trying to increase the awareness. We've done collaboration with many schools, especially with the English school, with the help of our colleague and friend, Dmitry, our space scientist at the Planetarium Observatory KITION, who is also a teacher at the English school. So we have joined projects and asteroid research campaigns with the school. And as you have seen, Cyprus now is in the international map for Asteroid Day as well. So this grew our interest in joining research projects and research programs. So international asteroid research campaigns, where this is a citizen science program. We bring students and other citizens or people who are volunteers here, and we search for asteroids. We have joined the Catalina Sky Survey, NASA. We are the national coordinators and national point of contacts for Cyprus, me and Alexander, for the International Meteor Organization. And we have made publications for the IEEE, the International Electrical and Electronic Engineering group. And we have published something there about asteroid research campaigns. And we try to enter the NEO Shield 2 project, the Near Earth Object Shield Project 2, which actually we're giving ideas how to deflect asteroids from input and avoid them from impacting Earth. Now, what you see on your screens is an extract from our project searching for asteroids. So you see here the red inscriptions here are the already discovered asteroids, and with purple color are the proposed actual asteroids that we have discovered in this set of images that we have gathered from the telescope in Hawaii. That we are using a 1.8 meter telescope, which Ukrainian. We see the cameras. They're taking pictures of the sky for different pictures, and we flip them. We're creating a video trying to search for moving objects. Up to now, we have proposed 576 proposed asteroid discoveries, but our first provisional asteroid that was given the name 2019 AN16 P10KOIJ, that was also in honor of our team published in America by the American Astronomical Society in their calendar this year, and it's you can find it on in April 2021 in the calendar of the American Astronomical Society. It's a great honor for us. So this is an extract from the picture from the software, and what you see in the circle is the actual asteroid, and here you can see the light curve of it, and here are the 5 people that was in the team that was discovered that day. So we give it a name in the beginning, KPO, KITION Planetarium Observatory 316. That was the 316th number of asteroid that we proposed. So this became our first provisional asteroid. It was acknowledged on the 1st of February 2019, as it was 13 days before our 11th birthday, 11th year celebration of the asteroid, and from the creation of the KITION Planetarium Observatory. Sorry. So this is where our asteroid is found. It's further away from Mars, and this is its orbit. So last year we have discovered another 2 provisional asteroids among the 576 proposed. The asteroid 2020 JW8 and 2020 PG26. And if I'm not mistaken, we have one more on the go. I have an email from NASA last week from Cassidy, and I'm trying to find time to have a look at it. So, talking about fireballs, this is a video from it's one of the testimonies. Have a look. Have you seen flash? Let us replay the video. Concentrate here at the top right corner to see the flash that was captured in the security camera. Have a look. This was a very large fireball that was observed on the 9th of September 2016. So our team has gathered information and many videos from all over the island, and a lot of testimonies. Encourage them to enter their testimonies at the IMO, International Meteorological Organization website, so we could come later and using this data, measure the speed and try to estimate the angle of attack, the angle of impact, and in the atmosphere, and try to figure out, calculate the height, if there was an explosion, if there are any pieces left behind and fell down as meteorite. We're still searching on it. And here is another camera. there is a bit of light on the top right corner, but you will see how the night was enlightened by this fireball. This is a camera from the school of KD. Have a look, and you can see, if you check the video, you can see the shadows moving, so you can calculate the speed. So a video which seems like not important could be actually very important for science. So these are extracts from our publication in the IEEE, KITION Planetarium Observatory Cyprus, international research programs concerning near-Earth objects. We have discussed our cooperation with Kiev, and our friend Gianluca Masi. We have discussed how we use technologies and to share knowledge and databases. We talked about our research projects, our public outreach programs, our meteor observations that we use. That we also try to do vast outreach regarding citizen scientists, and how we promote it with educational courses and programs, but also scientific research. So join us for Asteroid Day on June 30th, and we will have another live program. We will connect with Greece on the 26th. I will share our link. It's going to be in Greek, obviously, that event. So, but you can. Some of you already know Greek, Ash, for example, and Joy from Lebanon. So you can understand some Greek. The rest you will have to learn Greek for the 26th of June, but on the 30th of June, we will do it in Greek and English, hopefully. So I will stop here, and I would like to give a chance for Alexander to present to you two of our students that are doing a really, really great job regarding asteroids and fireballs, and they are very, very clever guys. They are great minds. Alexander.
Good evening, everyone. And yes, this story about the two students George started, it had starting last year. We made it like summer challenge for students. So some students come to us, and we started to make search about trajectory of asteroids. Of fireballs. So we have one fireball, another fireball. So some of them were observed over Cyprus, and we collected enough data from testimonies. And the main point is, is it possible to reconstruct the original trajectory of observation based on observations? And these two students, they will present their talk. So let's have a look. Proceeding of images with fireball photos. So Dmitry Dubishkin will explain us how the first part, how to collect data and how to increase the accuracy of this collection of data. Dmitry, are you ready?
Give me a few seconds, please. I have some technical issues. Okay, yes, I'm ready.
Okay, let's
Can I share my screen?
Welcome.
Can you see my screen?
Yes, perfect.
Okay. Nowadays I'm making a project about processing of image with fireball's position. Purpose of my project is to collect data from the images with fireball and try to reconstruct the trajectory of the fireball. Let me explain some of the theory. Let's say we have an observer at this point of the Earth. And we have here we have the field of view of this observer. He looked in the sky and saw the fireball passed by from these two points. And he made a photo of this part of the sky and sent it to me to process it. So my data is I have the location of the observer, and I have few locations, geographical coordinates of few objects that I can see in his photo. That like this. For example, I know this point at the photo and this one. Then if I know those numbers, I can calculate the angle between me and these few points. Let me show how I can do it. Based on using this equation, I give them the phi coordinates, this one, and lambda coordinate, and the result I can find this angle, and then I can find this the azimuth and the height of this point, which I know the geographical coordinates by using these two equations. This is the radius of the Earth. This is the height above the Earth of the one object, and this is height above the Earth of the other object. And here I get the angle. When I get the angles for two of these points, I can find an angle between them two. So this angle. And then if I know this angle and if I know the difference between their coordinates in photo in pixels, I can get the scale of the photo. How much degrees is going for selected amount of pixels, and based on this, I can get the angles for 2 points of the fireball's trajectory. Here I multiply the difference between two angles of 2 points by this scale which I found recently, and get some value in pixels for z coordinate, and another one for height. Then I get these two constant, and based on them I can get the angles for the fireball, for the points of the fireball trajectory. to make my task a little bit easier, I write a program in Python instead of making all calculations on my own in the piece as a piece of paper. And so here I have my data that I get from the observer and from my picture. Here is observer coordinates. Here is my A point coordinates and B point coordinates in geographical, and the heart above the sea. And these numbers, which you can see in the photo, is the pixel coordinate of these points. So 163 in this axis and 500 and this at this axis. Same goes for the asteroid points. And I give to my program this data, and by using the equations that I showed you in the previous slide, it calculates the angle at which the observer can see these points. After that, the program calculates the scale, how much degrees going to corresponds to the for one pixel, and after this it gives me the angles for these two points. If I could get more than one photo and find these coordinates for each of them, I can reconstruct the trajectory because that. Give me a minute, please. I forgot how we call it. One observer sees it from this location, and the vector of his view is going to this point. Another one, let's say, is located there. He's viewing this point from the other side, and there is only one point that is mutual for them too. And this is how we can get the coordinates. That's how we can reconstruct the trajectory of our fireball. I apologize for my English and I wasn't really ready because I have many exams now, and I don't have many time to work on the astronomy. And I would like to thank you, the KITION Planetarium, for providing me help with calculations and giving me the image from their archives. Thank you for your attention.
Any questions?
First of all, I would like to congratulate him. He's done a great job, especially writing in Python is not so easy. Very good initiative, and thank you for joining our team, Dmitry. We are very proud of you, and we are always here for you. It's a great job. It's not easy, you know.
Dmitry, that is very excellent work. I'm very impressed with that.
Thank you. I'm gonna develop my mathematics and my Python program in future when I will get more free time to do it. Nowadays, I don't have much of it.
This is a fantastic idea. I love it.
Thank you.
I think maybe the word you were looking for is triangulate, is it?
Triangulation.
Yep, yes, that's it.
Where you have two different observers looking at one object, and you find the point. It must be at that point. Yes.
Yes, we have one observer standing here, another one standing over there, and they're both looking in the skies, and their views making one we can imagine that it's making one line in the sky, and these two lines will be crossed only in one point. So if we get this point, for example, this and this, we can make another line that connects them, as that's actually the trajectory of the fireball.
Excellent.
That's what really new in this idea. It's Dmitry, could you leave this picture? Is that we have many testimonies from observers, and they describe it. For example, when they sent to IMO, and they describe it to us. They say, "Okay, it was there, there, there." So I could not say that it's not very precise, but I truly believe that this style just take picture of the area where the observer saw the event and put on that picture just 2 points where it begin and where the end. It is enough for our team, and Mr. Dubishkin presented now, that just with the rest of landscape landmarks, we could find out very precise position of these points that observer show on the picture. And what I believe is that when you see something incredible, you may not remember time when it happens. That's why you have to look at your watch, at your clock or watch, yes. And but all the rest, how it goes, what was surrounding and so on, where it fly, all this you remember till the end of your days. So it means that you would, these data are very, much more precisely to be collected in this way. And we have many, these days, mobiles, which could give you a picture very easy, much easier than even 20 years ago. Okay, some more questions?
Can I come in with a discussion on this? This business of triangulation is something I've been doing for a long time, using rocket experiments, and at the moment I'm starting to set up for some triangulation on noctilucent clouds, which are visible from the UK. Fortunately, from southern UK, noctilucent clouds almost always appear in the far north, so it's possible to use a camera with a reasonable field of view, maybe 45 degrees, and 2 cameras separated by maybe about 50 kilometers in order to get the triangulation and baseline. You're on an island, Cyprus. You need to have 2 all-sky cameras with quite high resolution detectors because you don't know where these asteroids are coming from. They could be coming in on any trajectory from any direction. So to have a reasonable chance of being able to actually get accurate measurements, you need an all-sky camera with a high-resolution detector. And then basically, of course, you need accurate timing so that both cameras and the images can be accurately given the time that the images are taken. But then, of course, the problem is to identify stars against the all-sky camera and use that basically to give you the fiducial reference instead of using geographical references to actually use the stars. So you measure the stars, the positions that are available from catalogs can be calculated for their positions in terms of from the right ascension declination and the sidereal time. Then you can actually work out exactly where those stars are in terms of azimuth and elevation, and that gives you the basis for the triangulation. If you want any help with the mathematics of that and the programming for that, I actually have all of that if you are interested in taking that further. So cross fingers, I'm hoping you are perhaps interested. I'd be quite happy to discuss this further with you. And as I said, I'm trying to start up some triangulation noctilucent clouds from the next few nights onwards, which is the start of the summertime noctilucent cloud season from the southern UK. So thank you.
That's great. That's great, David. Thank you very much. Alexander will have this in mind and we can contact David. David, I'll write down in the beginning of the chat, I have our contacts here. I will repeat, I will rewrite them down.
Yes, you have to rewrite because of David could not
see. So you may send us an email with this info, we can proceed further. Yes.
So this was
And
taught.
also, my camera is in the near future plans. Actually, I have some. We have some some leaflets here, and we are trying to find what is the best diameter and try to decide on the specs actually. How many millimeters should be installed regarding the place we are going to install it, and so on.
Okay, so this was.
Keep in touch, David. Thank you very much.
So this was a talk about how to collect data from observers and how to increase them much more than it was at the beginning, just with IMO reports, for example. And now we have another talk. Maxim Verevkin will present it, automatic analysis of the trajectory of a fireball. Maxim, are you ready?
Yeah, so 1 second, I will share my screen.
So I'll start sharing now.
Yeah, it's a little tricky because I use an operating system that has a little worse support from the Zoom. So, okay, and I will start sharing. You will see my screen in place of my image.
Actually, not like this. We should. It's not sharing. It is.
Unfortunately, I cannot share.
Yes, now it's okay.
Now it's okay. Try again.
No, perfect. It's okay. So everyone could switch their view into speaker's view. And then we may pin, for example, Max Verevkin, and that's all.
So, do you see my screen?
Yes.
Okay, so it's my first talk, so I might be a little stressed, but anyways, so automatic analysis of the trajectory of a fireball. Let's get started from the very beginning. Data sources. So whenever a person observes a fireball, they can report it to the International Meteor Organization database, where I'm online form on their website, and they report information such as their location, duration of the observation, descent angle of the trajectory, and the azimuthal coordinates of 2 points that they observe, the beginning of the observation and the end. Here is an illustration. You can see those 2 points on the sky, and this is a visual definition of the descent angle that we will use. So let's continue. The problem statement, it can be described as follows. Given n observations, we have to find a trajectory that suits observations the best way. The if observation has a form of geographical location of the observer, 2 points of the observation, the beginning and the end, the descent angles of the trajectory that they observe, and the duration of the observation. And we are allowed to make 2 simplifications. The first one is that we assume the trajectory is a straight line. And the second one is we assume that Earth is a perfect sphere. So we have only 2 major simplifications. And in order to say that one trajectory is better than another, we need to define some way to rate each trajectory. We will use the method of least squares to find the best trajectory. So each trajectory is rated using the sum of squared errors. What are those errors? Let's imagine we have some trajectory and we have the observer's data on the right, we can see it. Okay, so the red line here is the trajectory that observer told us. Then we have a trajectory in green color, and we project it to the sky of the observer. So we have three errors. The first one is the difference in descent angles. It's quite simple and straightforward. We just find the difference on those descent angles. And also we have LB and LE in these notations. They are the angular distance from those points that observers told us to our trajectory that's projected on the sky. It's in angles, and so we can rate each trajectory with a number, and the best one is with the least number. Here we can see a plot of S. Here we take a perfect answer trajectory on the simulated data, and we move it against the x-axis and calculate the error. And here we can see that the plot is not continuous. That's because when the observer looks at the different direction of the trajectory, he is not accounted in the sum, and that makes the search a lot harder because we have to check each local minimum in order to find the global one. So I have the implementation. Current implementation is written in Rust programming language. You can see the link. It points to my GitHub account with a GitHub repository. In addition, there is a random input number input generator for testing purposes and benchmarking. It generates a random trajectory and random observers who report their observations in ideal way without any mistakes, and then we can use this data to check if our implementation is correct or not. Right now, the accuracy is 0.33. It's not perfect, it's still not perfect, but it has improved in the last days, and we can make it even better, of course. The project structure is quite simple. There are some files missing here, but the main one is src/solver.res. It's the actual search algorithm implementation and the evaluation function called S in the previous slides. The search algorithm is split into phases. Phase one is like a rough estimation. So we initialize the search range, is the range of all possible trajectories. So it's a cube in the space with side left for several hundred kilometers. Then we can choose n random trajectories from this range. For example, 10,000 or more, like a million maybe, but it will be slow. So we choose some number of trajectories and we select the best one of those. The best one meaning is it has the less error, the less sum of squared errors. So we find a trajectory with the least error, and then we store it in some kind of variable. And now we can continue to the phase two. The phase two, in the first point, we have to generate a new trajectory from the previous one. So we take the stored trajectory that we got on the previous phase, we copy it and modify it a little bit with some variants. So what does it mean? Is that we get the previous trajectory and move it around those axes and rotate it with some variants. And then we rate the resulting trajectory, and if its error is less than previous, we override the stored trajectory with a new one, and then we repeat this process several hundred times. For example, 100 and more. The more is better. The accuracy will increase. After those iterations, we can decrease the variance for more precise answers, and then we can continue this whole algorithm again, maybe 10 times, maybe 20. Again, the more is better. And then what we are left of is the result, the trajectory that we hope describes the best those data that we have. And then again, current accuracy is 0.83. It can be better, but for now it's like this. And so that's about it. And future plans, of course, is to increase the accuracy on ideal input up to 100%. That means that every time I run algorithm, it should find the answer, given that data is perfect. Next is to develop an implementation on data with observers. That means to test the program on real world data from the real observers and make it work, of course. And then I hope it is possible to develop a more efficient search method. Right now, it is not that efficient. I mean, it's like 1 second per 200 observers. It's quite fast, but it's not as fast as it could be. So that's it. Thanks for your attention.
Do you have questions?
I would like to congratulate Maxim. Maxim, how old are you now? Maxim.
Excuse me? Yeah.
How old are you?
I'm 16.
Now, I wanted to mention this because it is an incredible job from a 16-year-old guy who has all the future in front of you. Great job, excellent, great mind.
Thank you.
Thank you, Max. This is great.
Well done, Max.
Thank you.
Yes, congratulations. A very good job. See where we go from there.
So right now we started to make search of a trajectory of a fireball which was over Cyprus, as Maxim shown in 2020, 21st of January. That time KITION Planetarium and Observatory collected all over Cyprus more than 200 reports. It was an incredible result, and that's why we choose 200 observers every time Maxim asks computer to simulate process. So, idea is how to proceed with them. Definitely 200 is a lot, and there could be some data hidden inside. Moreover, the fireball was so bright that it is recorded by NASA as well from the space. So we have we know precisely the coordinates of this fireball taken from spaceships. The event was registered. So we wanted to know how it is connected our program about working with database of observers with their testimonies together with the real data which we know for sure because of the event was photographed from the space. So we know the answer precisely, and we know we have 200 reports. So it means that based on this, we could develop a program which will work with it. And we find out that all our estimations finally came to the first point because of the because of the sum is not even, it's not linear. It has always, as Maxim shown, local minimums. The whole sum is always has this minimums, local minimums, and that's why it is. So even if we find out this trajectory, what if we are in this local minimum, and we did not find the precise trajectory. So that's why we started from practically from beginning. So we started, and Maxim now reports the working out only the program. Let's suppose that everyone without errors make the correct answer, give correct observations, and we name it ideal. And so when our program will bring us 100% trajectory, it will answer yes. Yes, precisely, there is this this very trajectory. It's for sure correct if we have without mistakes observers. So after that, the next point, of course, is to work out with these 200 people and find out the program which will bring us to more or less good outcome. So that's our next future. Okay, what we have next? Just in few days, we have total, no, just annular solar eclipse over large part of the world, and it is the very first time when I see that eclipse goes precisely in the North Pole. So this is the North Pole of the Earth, and here we may observe annular, unfortunately, but solar eclipse. If you see on this map, there is no chance to see anything from Cyprus, and there is very tiny chance to see something from Oleg Kriklev. Now he is in Ukraine, and Jim Wiggins is somewhere here, if I don't mistake, here.
That's very correct.
Okay, so I visited Barcelona some time ago. Well, and so here it will be something like 3% phase. And my very first observation of solar eclipse was 3% as well. But now I'm in Cyprus, so no chance at all. Well, and as in the Great Britain, we could better chances, and the best to see just arrow ring of fire, as I used to call it, is somewhere on this path. So at the bottom, you see a Facebook translation of this event. It will happen. The translation is of Astronomers Without Borders, but it's not the only organization. It's just an example if you didn't find others.
If you go to this link, you will find around 20 links worldwide.
So yeah, so it's not the only one, but anyway, it was to make online observation for those who are not in the region.
And we are expecting photos, Alexander.
Yeah, from Cyprus.
I don't know from who, Jim, but you can guess.
From Cyprus.
Actually, some people in Cyprus, they were trying to organize an event, and I was wondering how could they observe it, and I told them, guys, it's not observable from Cyprus, only the internet.
Okay, so and our next event is, Science Cafe event is on Tuesday, 22nd of June. We will invite our old friend, Dr. Iris Harlambido, and she will give talk about plastic pollution over time and space. And it's part of her life, as I could guess. Iris, would you like to say a few words?
Like I explained to Alexander, I obviously cannot talk about anything to do with outer space because it's not my area of expertise. And so since KITION Planetarium kindly invited me to give a presentation, I thought I would talk about something that's going on planet Earth and that has actually reached some of the most extreme places on planet Earth. So this is a hot topic actually of our times, the presentation that I want to give. So that's it. So it's about how far plastic pollution has reached on our planet, and also for how long certain types of plastic will remain in the environment. So you're going to hear about that in more details in the talk.
Thank you. Thank you
We are
very
looking
much.
forward to it.
Pardon?
We are looking forward to it.
Oh, thank you. I'm looking forward to it
I'm
too.
sure it's going to be a very impressive one, and we are looking forward to the next one, about the human evolution, which was really impressive last time as well.
Well, thank you. Thank you. It was nice giving a talk actually at the KITION Planetarium. It's nice to be invited.
Great honor for us.
Thank you.
You may compare the plastic pollution on the Earth to the plastic pollution on Mars, maybe.
Yeah, you know, I was wondering about that because unfortunately, I'm imagining that we are going to be leaving some plastic on Mars as well now. So I was wondering about that. I don't have any information about it, but unfortunately, I mean, it's exciting to be exploring another planet, but unfortunately that some of the drawbacks are the pollution that's probably going to be left behind on another planet, which is, in my opinion, it's quite sad actually. Because I'm an ecologist, so, and I deal with environmental issues, so that's the downside of exploring another planet.
Okay, thank you everyone for visiting the Science Cafe, and we'll meet again in 2 weeks.
I have a proposition for my friend David. David, can you hear me? Mr. David Rees?
Yes, I'm here.
Yes. So I wrote my proposal here on the chat. So, since would you like to give us, since we're trying to increase the awareness about meteors and asteroids and meteorites, but okay, since you are dealing with all sky cameras, is it easy for you to prepare something for us for a future online event to present to us what an all sky camera can do and share with us some of your observations, the technologies used? So maybe we can intrigue some people here and they can use them, and maybe we can grow the network.
Yes, I mean, I do give quite a few Zoom talks on a range of topics. So yes, I'd be quite happy to prepare something on this. I think you have the prospects in Cyprus, much better weather, for example, than we have in the UK. There has been a network running around Western Europe trying to take good images from multiple sites of fireballs. I've been a little bit involved with that, and I could get more information on exactly what that's being done. But given the weather conditions there, and given the fact that technologies are moving on very rapidly as far as cameras, for example, are concerned, I could give you a very good description of just what would be required at 2 stations in order to make some really excellent measurements of fireball events. And you obviously get a few of these per annum, so that should be plenty of information to start keeping people busy processing data, which is quite time consuming. You're tracking from probably about 120 kilometers with a big object down to 30 kilometers, 20 kilometers, where there would be this big explosion where they disintegrate, except the very large ones disintegrate. So you want to cover that entire range. That really means we're getting a baseline of the order of between 50 and 100 kilometers. And that's not too far from what we're using with the ATV-1 re-entry. I mean, I've done triangulation on hundreds of rocket experiments over the years, chemical trails and grenades and things like that. But with the ATV, we're using 2, or in fact, several cameras on 2 aircraft, tracking basically parallel to where the ATV was going to be re-entering over the Pacific Ocean. And really, the whole experiment is very, very successful. Only one object actually splashed in the ocean. We were able to make a very careful prediction of exactly where that did from being able to see that event and then tracking the separation of basically the attachment ring, 2-ton attachment ring holding the ATV onto its rocket. And of course, that basically 2-ton titanium attachment ring did not burn up. Big splash when it landed, but of course it was really, well, something like 2,000 kilometers away from any inhabited areas, so quite safe. But of course, NASA and ESA really wanted a very clear indication of where all the objects coming from the ATV-1 actually entered the atmosphere, and the fact that most of them did actually burn up in the atmosphere. We tracked about 200 objects in total coming from the ATV-1 re-entry. So that gives you an indication of what happens when a 20-ton object actually comes in to the atmosphere at, in this case, only at 10 kilometers per second rather than the much higher velocity of the average fireball. But it's still enough to produce a pretty good fireworks display. I could send you a little write-up on just what we did for the ATV-1 experiments, and perhaps we could take that up then and consider a talk in the future.
Yes, yes.
Okay.
Very interesting. Very interesting topic.
Okay, thank you.
Yes, we will contact.
Yes, I sent you my email on the chat.
Mm-hmm.
Otherwise, the people at Wielden, including John Fox, know me rather too well.
You know that Chinese launcher that just fell back to the Earth, didn't that just sort of pass right over Cyprus just before it landed in the Maldives?
South of Cyprus, over Egypt.
Ah, okay. So you weren't able to see anything.
A few hours before, the Greek army and the Cyprus army was alerted, you know, showing off on the TV. As if they were going to shoot it. I don't know what they were.
As a matter of interest, perhaps, I persuaded John Fox to actually go out with a camera that night and try to observe it from the south coast of the UK. I don't think he actually managed to observe it, but I was sort of extrapolating that on the orbit that it actually re-entered, it would be down around 120 kilometers and descending quite rapidly. At 120 kilometers, so an object of that size would actually be relatively bright. The problem was he was trying to observe it with average British weather, and it was only about 3 degrees, 4 degrees above the horizon. Very, very difficult, very challenging. But of course, John's always up to that sort of challenge.
Yes, unfortunately he couldn't. He was in Brighton today, so he couldn't attend the event.
Yes, I was looking for him on the.
He sent me a message. He texted me 1-2 hours before the event.
Oh well, I think at least another one of the Wielden people is on the call, so I'm sure they'll brief John later.
Yeah.
So, no, congratulations. An interesting talk, and very good to see the contributions from your 2 students.
Yes,
thank you, students.
Thank you.
Dmitry and Maxim, people are saying thank you.
Yeah, thank you.
Thank you very much.
It's our honor to have so good students, and these people, they are dedicating time from their own free time because they want to proceed further from what they learn in school. And actually, it's one of our missions to intrigue the students and encourage them to deal with the world of space exploration and science in astronomy and astrophysics in general. So we feel proud about them.
Yes, well, congratulations to Max in particular.
And I would also like to congratulate Alexander, who is spending a lot of time with them, because lately I spend no time with them at all. And Alexander is doing a great job.
Yes. Regarding Max, it reminds me of something I did at his age. I was supposed to be doing a physics practical, and I told my physics master where he could go, that I was going to go to the local observatory and watch the occultation of Regulus by Venus. That far more challenging because that was, of course, long before the days of go-to systems. So it's far more challenging and difficult than what he had planned for the physics practical. It worked as well. For once, it wasn't cloudy over South Wales.
Oh, excellent.
Astronomy is very interesting. So, thank you very much, guys, for being with us tonight. I'm repeating that if anyone wants to share their own presentation with us, to want to give us a talk, you are more than welcome. Ash, Jim, Raleigh, Victor. Our friend Victor is also national coordinator for Asteroid Day. He connected earlier in the beginning. He reconnected now. Thank you, Victor, for trying to connect with us again. I promise that I will load up the video. I will upload the video very soon. Very soon means next week. Huh?
Thanks, everybody.
You're very welcome. So, see you in 2 weeks' time. And listen to what Iris has to tell us about plastic in space and time.
Yeah.
Great.
Cheers all. Bye then.